Hello guys, I'm audible. All of you can hear me. So all of you can able to see my screen. So in the last class we have seen that viscosity, and we have discussed that is one of the property of the fluid. Yeah. So very good evening to all of you. So we have discussed the fluid which follows the Newton's law of viscosity will be called as Newtonian fluids, and the fluid which does not follow the Newton's law of viscosity, that is non-Newtonian fluids. Just wait. So note down one more term, kinematic viscosity. Kinematic viscosity basically in fluid mechanics and heat transfer, it is one of the very important term. Generally, remember whenever you do the research, when we suppose we are working in any organization and we are writing any number of equations. In that number of equations, many times we will be getting the different parameter, like sometime we will be getting viscosity, sometime density, sometime thermal conductivity, sometime we will be getting omega, for example, right? Angular speed if it is a dynamic fluid. So many time we used to get different types of different elements or parameter in the equations, right? And it will be very difficult for us to solve those equations, right? Of course we can get the solution, but that will take some good amount of time. Generally whenever the terms is coming like mu by rho, right? Generally whenever the term is coming mu by rho, we directly replace it by kinematic viscosity. Only for that purpose we have extra term in our fluid mechanics or heat transfer, that is kinematic viscosity. There is a no any other reason. If you ask me, sir, why there is a, if dynamic viscosity is there, then why the kinematic viscosity it is present there? So that is only the reason I told you, right? So it's basically all the definition which is given by the researchers, when they started doing the fluid mechanics research during the 16th century, right? So what I will be suggesting you that we cannot do much in that. We cannot go back to the history and see that what is a region or region for origination of these parameters. So directly, blindly we have to trust that whatever the research they have done, that is accurate. Now here you just note down, it is the ratio of the dynamic viscosity to the density, right? That is called as kinematic viscosity. Now that is a very simple definition. I can directly tell you without telling you the 5 minute history of that. But again, you might be thinking, okay, that is a separate term which is being defined in the fluid mechanics at the starting only. No, it is not like that, right? So to give you idea about that, I have just told you this thing. Now, what is a unit? So unit of viscosity, we know that Pascal second, and density will be kilogram per meter cube. So when you see this, I'm talking about the SI unit, then Pascal second we can write further as Newton per meter square second divided by kilogram per meter cube. Once again, I'm writing from here to here. What is that? Newton. 1 Newton. Further, we can write kilogram meter per second square into second divided by kilogram per meter cube. So when you try to solve this one, you will be getting meter square per second. Make a note of it. That is a SI unit, right? And if I will be asking you CGS unit of kinematic viscosity of nu, then what you will write? The CGS unit will be what? Centimeter square per second, right? And 1 centimeter square per second will be what? 1 centimeter square per second will be 10 power minus 4 meters square per second. And what we can write this one? Anyone know that? Any other specific name is there for that? 1 Stoke will be equal to 10 to the power minus 4 meters square per second. Make a note of it. And in terms of dimensions, what we can write? Meter square, L square by T. So what we can write? Like this. So 1 is Stoke. Stoke is nothing but CGS unit of kinematic viscosity. So if further we used to get the question like this: what is the difference between dynamic viscosity and the kinematic viscosity? So dynamic viscosity, when you see that, how to determine the dynamic viscosity practically, we have to take the fluid element in a container and then we have to rotate it, right? And whatever the deformations rate will be there, and whatever the amount of shear stress we have applied into the container, then if you just divide those two terms, I will be getting the viscosity. So with the application of the external force, we are measuring that one. Which one? What we call dynamic viscosity. But here in the kinematic viscosity, if I want to measure for any fluid, directly I will not be applying the shear stress, right? It is just being rotated with the help of maybe some gravity, right? For example, and in that case, directly I will be measuring the deformation rate, and I will take the basically the ratio of what the actual dynamic viscosity of that particular fluid to the density of the fluid. So that will give me directly kinematic viscosity. So why the name itself is coming over here, kinematic? Because there is no particular force has been involved, right? If you see the unit also, meter square per second, right? There is no such a term called Newton there. But when you see dynamic viscosity, that is a Pascal second, right? So that is there the term involved Newton. So that's why the name is given dynamic viscosity, right? Now make a note of it. Now, one drawback of my teaching is something you might be, you may be thinking that, sir, in all the subjects, the particular topic, we have to learn like this only, right? Uh, we have to go back to the history and fundamental concept, then numerical. But I will be suggesting that do not do PhD in any particular topic. That is my first suggestion. If you do PhD with less number of numerical, you maybe end up getting only 40 marks or 30 marks. Sometimes you may not be able to clear the cutoff also, right? So please, whenever it is required, then only do the PhD, otherwise it is not at all required, right? Because you might be thinking, right, that is a temptation because of my teaching, right? So that is what I'm just you can consider it like a precaution. Only fundamental thing has to be clear, plus you have to solve enough amount of problem regarding that particular single topic. Remember that. Now, all of you have noted down? Can I move to the next one? Okay. So here I would like to tell you the reason of viscosity, right, in liquid and gases. So note down the first topic. reason of viscosity in liquids. What is the reason of viscosity in the liquids? Anyone know that? So liquids and gases, if I just say, so they are basically two major, you know, factor or mechanism responsible for the viscosity. Two major, what we call factor or mechanism responsible for viscosity. So one will be definitely, I know everyone know that. I just categorize into two. One will be the cohesive force, right? One will be the cohesive force. Like you know that cohesive force, adhesive force, like that. Here we are telling about the cohesive force or molecular bonding force. Molecular bonding force between the same kind of molecules. Second mechanism, we will be having mixing or molecular momentum exchange. Molecular momentum exchange. So basically, if I'll be talking about the liquid case, in liquid, which one will be responsible? This will be responsible. For the liquid, the major factor which is responsible for the viscosity is nothing but cohesive force. In case of gases, this is the basically responsible. See, don't think that in liquid only cohesive force is there. There is no momentum exchange. But out of these two, the major which is affecting the reason of viscosity is that, or the reason, accurate reason that is responsible for viscosity is cohesive force between the liquid molecules, right? Again, molecular momentum transfer is also happening in the liquid also, but that is less dominating as compared to cohesive force. Again, in the gases also we have the cohesive forces, but that is less dominating as compared to mixing or molecular momentum exchange, right? Make a note of it. Now we have to see, my dear friend, the effect of temperature and pressure on the viscosity of the liquid and gases. For fluid mechanics, to understand completely, you should be finished your differential equation. That is a mandatory. Otherwise, always you will struggle in partial differentiation, partial integration, why constant has not been added, why some other arbitrary variable has been added. So all these doubts should be there, but please make sure that you clarify from the mathematics, because fluid mechanics is nothing but mathematics only. It is just added that we are doing the mathematics of, not the numbers. We are doing the mathematics of fluids. That's it. Why? Because I have seen in the last, particularly, for the GATE 2023 batch, some of the students, not all, one or two students, they are doing actually, always they used to get the doubt. Doubt is genuine, but they used to do PhD in every topic. They end up getting only 26 or 28 marks only. So there is a no use of that. All those research work you can do after getting good rank in GATE exam. Now, once it is done, let me know. Done. Done for all. Okay. So note down the effect of temperature and pressure on the viscosity of the liquid. What are all the effects will be there of temperature and pressure on the viscosity of the liquid? Now, what will happen when I increase the temperature? Tell me, guys. Whether whatever the cohesive force is there, that will decrease or increase. So, viscosity of the liquid will decrease. Now, why it will decrease? Because cohesive forces between the molecules, because cohesive forces between the molecules, between the liquid molecules decreases. Right? Correct. Whatever the bonding force is there, that will decrease, and that will decrease the viscosity, right? So if viscosity will decrease, definitely flow will be very, very easy for us, right? The flow will be very, very easy for us. Now, what will happen? Simultaneously, I'm discussing for the liquid and gases. So when the temperature will increase, what about the viscosity of the gases? So basically, when you see that viscosity of the gases, generally it will increase, right? Because when I increase the temperature, then molecular momentum exchanges will be very, very high. Because molecular momentum, the in a container, when you try to increase the temperature, right? Definitely you are trying to giving the energy to the molecules, and the gases molecules, they will try to collide with each other molecules, and they will try to impart the whatever the whatever they have the velocities, right? So definitely there's a lot of momentum exchange will be there, and the viscosity of the gases will decrease, will increase. Now, because the molecular momentum exchange will increase. What about the pressure? When I increase the pressure, what will happen to the viscosity of the liquid? So generally viscosity of the liquid will remain same. Generally remember that for a very, very 1% or 0.5% only, 99% of the cases, the liquids are highly incompressible, right? Even though you put elephant on that, they will not be getting compressed, right? There will not be any chance of decreasing or increasing the bonding forces, right? So make a note of it. When you try to increase the pressure, then what about the viscosity of the gases? Once again, that will be same or different. Once again, it will remain same. Once again, it will remain same, right? Why it will remain same? Because molecular momentum exchange is directly proportional to root mean square velocity, right? Root mean square velocity will not be depending on the pressure. It will directly depending on the what? Temperature. Remember that. It will be directly depending on the what? Temperature, right? So if I write the formula of root mean square velocity, that will be 3 RT by m. So it is directly proportional to temperature, right? Yeah, that is a kinetic energy, right? That is according to kinetic theory of gases. And more sources are suggesting that according to kinetic theory of gases, according to kinetic theory of gases, that is for ideal gas, when you just apply, viscosity will be directly proportional to temperature, and kinematic viscosity will be directly proportional to T square. I'm talking about the gases. Make a note of it. So this is the another proof. One proof is this one, second proof is this one. So both the proofs are suggesting that it is independent of the pressure. Under root of, sorry, this will be under root of T, and this will be 3 by 2. This has to be corrected. Yeah, 3 by 2. Whatever the randomness is there in the gases, that will be coming because of the velocity only, and that velocity will not be changing because of the pressure. Remember that that velocity will not be changing because of the. Yeah, I will discuss, Ravi Tej, I will discuss. Now, so whatever the momentum exchange will be there, that will be directly proportional to what temperature. That will not be proportional to what we call pressure. Is it done for all? Now, so the next concept will be, if I increase the temperature, then what about kinematic viscosity of the liquid? Then what about the kinematic viscosity of the liquid? Whether it will increase or decrease. So when you think of this one, this particular case, what you are observing, mu by rho, right? So mu of liquid is decreasing, and the liquid case, when you increase the temperature, I'm not talking about the water. For a very general case, we have observed that for a fixed pressure, for a fixed pressure value, when I increase the temperature, that means I'm fixing my pressure value. So what you are observing at a very, very low pressure, then what will happen? The density will also decrease, right? Then what you are observing from here? So we cannot say about this one, right? We cannot say the kinematic viscosity of the liquid. We can't say exactly what is happening with the kinematic viscosity of the liquid. But in generally, it has been found experimentally that kinematic viscosity of the liquid slightly decreasing on increasing the temperature. Yes, yes. Because anyway, a effect of density, whatever the effect of density is there, hardly any effect is there, right? Hardly any effect is there on the density changes when you try to increase the temperature. So it totally depends on the dynamic viscosity, right? Now, the density difference, or we can say the temperature will increase. Then what about the kinematic viscosity of the gases? Then what about the kinematic viscosity of the gases? Will increase or decrease? So for that we have to write rho of gases. So automatically this is increasing, and density of the gases is what? P is equal to rho RT, right? For a fixed pressure, for this one is to be fixed one, this will be what? Inversely proportional. So when I increase the temperature, the density will be what? Decreasing. So both are contributing to increase rapidly the kinematic viscosity of the gases, right? Further, my dear friend, the pressure value. When you increase the pressure, what about kinematic viscosity of the liquid? Tell me, guys. Yes. When you try to increase the particularly, mu by rho, mu of liquid by rho of liquid. Now, but you have to very careful. The pressure does not basically what? Increases or decreases the density of the liquid. It is incompressible, right? No change. Maybe any changes will be there, that is 0.5%, right? And this will also be no change. So what we are observing? No change, right? Correct. What about the, yeah, perfect. What about the, when I increase the pressure value, then kinematic viscosity of the gases, mu of gas by rho of gas. Mu of gas is what? Increasing or decreasing? For a fixed temperature, when I just increase the pressure value, my dynamic viscosity is increasing or decreasing? Tell me, guys. This is to be what? No change. Once again, as we have discussed earlier also, as you can see here, that dynamic viscosity of the gases will remain same, right? So here also it will be no change. Further, what about this one? For a fixed temperature, pressure is what? Directly proportional to density. For a fixed temperature, right? So what we can have, this will increase, so further it will decrease the kinematic viscosity of the gases, right? Make a note of it. So whenever we try to do the any experimental kind of thing, we try to vary only one parameter, right? We don't vary both the parameter. Now you have the wild thinking, sir, when what will happen when I change the pressure and temperature both? Then again, it is very difficult to predict, and you can't perform the experiment also. Getting my point, all of you? Because some of the students again they will waste the time after the class, sir. They will be start thinking, in a spacious world, that, sir, what will happen when I increase the pressure, decrease the temperature, decrease the pressure, increase the temperature, and they will start playing like that. So please don't do that. Getting my point or not, all of you? These are all I'm telling you based on the experience, basically what experience which is being faced by these students. So try to stick with the content which I'm telling you regarding fluid mechanics. That will be more than sufficient for GATE exam. Because at the initial phase of the preparation, you can think of topic, you can have some imagination, some thinking, but after certain point of time, when the time will be passing, and when the July or maybe August month will be coming, you cannot invest that much amount of time in theoretical portion. Lot many subjects will be there, right? Again the student will be start getting getting panic during those time, and some of them will be start demotivating, and they will leave the preparation, and they basically what, coming again back to in the month of what, December and January. with the so much of expectation that I will be getting good mark, but practically that is not going to be possible. Now, is it done for all? Can I move to the next one? Done? No. How many of you have tried that particular question which I have given to you? This one. Anyone got the answer for this question? Now, so what they are asking, what is the velocity at the interface of the, you know, flow condition which is being imparted? Anyone has tried this one? So when you see this one, they have directly given the two immiscible, incompressible viscous fluids having same density but different viscosity contained between the two infinite horizontal parallel plates 2 meter apart. The bottom plate is fixed and upper plate is moving with the velocity called 3 meter per second. Correct. 1 meter per second is correct. With the assumptions of the Newtonian fluid steady and fully developed laminar flow, with the zero pressure gradient in all the directions, the momentum equation simplifies to be d square u by dy square. Now, when you see this question, they have asked in GATE exam in mechanical 2019, but this question has directly taken from Single, unsolved. When you see the laminar flow or the Navier-Stokes equation, in that particular chapter, whatever the unsolved is there, directly they have copied from there, right? So we have to follow certain standard textbook so that we'll be directly getting the question from there itself. So what is the meaning of this? When I do the double integration, after double integration, I will be getting u is equal to c1y plus c2. That means u will be what? Varying linearly. That is what they want to tell us. Now, when the u is varying linearly, basically what? Linearly, my dear friend, then how will be the velocity profile for that? So when you just look at this mu2, what? Lower fluid which is having the viscosity twice, right? That means what? Whatever the du by dy will be there, the velocity profile for the second case will be lesser than that for the same amount of shear force, or the viscous shear force. Now, so definitely second fluid will be having less velocity gradient as compared to the first one. So what we can have, we can draw the velocity profile something like this. Now make a note of it. This will be theta 1. This will be what? Theta 2. This is what? This is theta 2. This is theta 1. Theta 2 is what? Less than theta 1. When you observe from the vertical, that is being observed. But the question over here is, what is going to be happening, right? What we have to find, the interface velocity, right? The top plate velocity has been given as 3 meter per second. So what we have to do? So when you draw the free body diagram of the mid plate, middle, or basically what? When you draw the free body diagram of the interface, so draw the basically what? Draw the free body diagram of this particular interface. So what you will be getting? Yeah, that is correct. Based on putting the boundary conditions, you can get the answer from there itself. Getting my point? But I'm telling you some other way through which you can get the answer once again, right? So here, free body diagram of interface, when you draw this one. So I'm drawing over here. Mu2, mu1. This is what, we are applying the forces onto the top plate. What the interface will do, it will try to apply some kind of force in these directions, right? And I told you, whenever we have the linear velocity profile, Always remember each and every fluid layer will be subjected to same kind of shear force. And what about this plate? Plate will offer force in this direction. And you also know that, my dear friend, you also know that fluid is not accelerating. That means the net force in the direction of motion. In the engineering mechanics, you have done right. Newton's second law. The net force in the direction of motion is what? Mass into acceleration. And for this particular plate, for the middle one, what you are observing, you just think it like a plate, interface plate, or maybe intermediate plate. What you can have? Tell me, guys. Acceleration is zero because every fluid is what? Moving with some constant velocity. Then what we can write? This F1, whatever is there, let's suppose F1 minus F2 will be there, zero. Then what about F1? What about F1 and F2? How to find that? What is the formula for the viscous force? Mu into du by dy into area. Getting my point? F is what? Tau into area, right? Getting my point? Now what we can draw, my different? What we can find out the F2 value? F2 value we can easily find it out something like this. Let's suppose this is the interfacial velocity u, this is v, 3 meter per second, and this is 0, right? So what we can write? What we can write, my different? Force 2 we can write. Force 2 we can write what? Mu into du by dy of second fluid into area. What is the area? Let's consider the area to be what? What they have mentioned the area. Area I can consider whatever the width will be there. Width I can consider it as a 1, and the length of the plate to be, let's say, L, right? And what about force 1? Force 1 will be mu1 into du by dy for the second for the first fluid into same area, So what about force 2? Mu2 into du by dy will be what? U. Tell me, guys. U divided by what? Gap. What is the gap between the plate? 1 and 1 into area. And what about force 1? This is the total velocity, right? And this is what? Intermediate plate velocity. Then what about this one? V minus U. So mu1 into V minus U by 1 into area. Now try to equate F1 minus F2. F1 is equal to F2. So what you will be getting, my dear friend? Mu1 into what? 3 minus U divided by 1. That is mu2 into U divided by 1. Mu2 is what? They have given 2 times of mu1. So what we can write? 3 minus U, that is 2 times of U. So what we are getting? 1 meter per second. When you draw the velocity profile to be something like this is wrong. When you draw like this, they will not be having a constant slope. Remember, this is wrong, right? They will be having different slope because I told you for the same CFOs, viscosity will be inversely proportional to du by dy. Higher the viscosity of the fluid, lower will be the tendency to flow easily. Correct. All of you are getting my point. So this is what they have given the equations. Remember, we have to write F1, right? Mu1 into theta 1 into what? Area. Theta 1 dot. D theta by dt, right? Basically, we used to write slope rate, right? Not the basically exactly the slope, right? Because exactly without rate, we used to write in case of solid, but this is a fluid, so d theta by dt will be coming. Getting my point, all of you? Once it is done, let me know. Can I move to the next one? Now, so again, this is a very simple question. The viscosity of the liquid decreases with the increase in temperature because decreased cohesive force. Yes or no, guys? Yes. This we have discussed. This also we have discussed. Now try to solve this question. No, again you will say, sir, chapter number 1 is not that important for the aerospace. But what you will say when they give for 2 marks? Again, sir, again you will answer me back that, sir, I will leave this question. How many questions you will leave like this? So you have to prepare. When the things are very simple, you try to prepare. Don't skip that. Put some effort. Definitely, you will be getting the, you know, answer for that question, right? Simply leaving that, sir, I am not going to study that because it is a very tough topic. Then definitely you will be not be getting a good rank. Because if you are not working hard, definitely someone is there who is working very hard, right? So whether you will be in the 21st century, 22nd century, or maybe 30th century, competition will always be there. Consider a solid cylinder housed inside the another fixed cylinder, right? This outer cylinder we might be thinking of, this is a fixed one, for example. Now, as they mention also, is stationary cylinder. The radius of the inner cylinder they have given as 1 meter, and the height they have given it as 2 meter. The gap between the cylinder is filled with the gap is they have given what? The gap they have given as 5 mm with the viscosity 10 to the power minus 4 pascal second, right? The inner cylinder is rotating at the constant angular speed omega, that is 5 radian per second. With while the outer cylinder is stationary, the friction at the bottom surface can be ignored. That means uh, there is a very good meaning in that. The friction at the bottom surface. That means this one. The friction. See, the fluid is there here also. The fluid is here also is there, right? So definitely you will be having the linear velocity profile like this. But the fluid is here also. But they have mentioned in the problem very clearly that we have to neglect that this bottom surfaces, right? So only we have to consider this side one. The velocity profile in the gap, that is the correct answer. The velocity profile in the vertical gap, they have clearly mentioned that linear one. When they mention already they mentioned that linear, so we have to assume the linear velocity profile. They are asking what is the driving moment required for the inner rotating motion of the cylinder in Newton meter, right? So once again we have to determine the torque, how much of torque I need to apply, right? So make a note of it first of all, then we will discuss. So very first of all, everyone know that the fluid is there. The fluid will offer some kind of resistive force, and to avoid or to basically balance that resistive torque, we have to apply some external torque so that it can be rotated. Otherwise, definitely how much amount of power I will give, if I give the less amount of power not equal to resisting power, then what will happen? We may not be able to rotate that cylinder with the constant angular speed, right? So yeah, so the net torque must be equal to I into alpha in the direction of motion. But we know that I into alpha, angular acceleration, that is d omega by dt. I believe that engineering mechanics they have covered this one. Now omega is what? Constant. Omega is constant means what? D omega by dt will be 0. The net torque means what? Applied torque. And in the opposite to the direction of motion, the resisting torque will be acting. That equal to 0. So applied torque, whatever we have to find, That should be equal to resisting torque. That should be equal to resisting torque. That is our very first thing that we have to understand. Now make a note of it. Now you try to understand what I'm telling to you. If I draw once again cylinder, and when you just look at very carefully this one, what you are assuming that here, that whatever the gap is there, right? We are assuming the gap to be whatever the gap is there, that gap is a linear velocity profile. And what we are thinking about certain this case, what you can think of some the case is, if I draw the resisting torque, what is the formula for the resisting torque? Force into radius. Now what is the force? What is the resistive force? Mu into du by dy into area into radius, right? But the big thing, the big question mark over here is that we have to understand there is a linear velocity profile, my dear friend. So you have to understand, we can write v by h, whatever the gap is there, v by y we can write into area. What is the area on which it is acting? What is the area, my dear friend? It is acting on a complete length of that cylinder. What is that? 2 pi r into L. That is the area on which this liquid is offering some kind of resistive force. So what we can write? 2 pi r1 into L. And the radius will be what? My dear friend, we have to take the moment about this one. Then what about the air moment radius? That will be once again r1. But the big question, mark over is that, do we need to perform any kind of integration? No, right? Because radius is not changing. When you look at from the point of rotation, this is the point of rotation, right? This is the center for rotation, center of rotation. And we have to take the moment about center of rotation. For every fluid layer is having the fixed radial distance, right? Fixed radial distance. So we need not to perform any kind of integrations, right? We need not to perform any kind of integration over here, right? Remember that. So that's why we are taking this one. Now again, area, you might be thinking, sir, area we can consider 2 pi r1 into L, 2 pi r2 into L. That also can be considered. Sir, 2 pi, in a better sense, sir, it should be 2 pi r1 plus r2 divided by 2 into L. Frankly speaking, that should be the value. But they have given the gap very small. Even though you try to put the value of r2, what is that r1 value? What r1 value they have given? 1 meter, right? 1 plus 5 mm, right? When you add it, you will be getting very low value, right? It is almost equal to r2 equal to what? R1. So directly I can write 2 pi r2 into L, or I can write 2 pi into r1 into L. The result will not change, right? So now when you just put the value, this will be my applied torque. That will be my resisting torque. That is mu into V will be what? R1 into omega. Inner cylinder is rotating with the speed of what? R1 into omega divided by gap 5 into 10 power minus 3, 2 pi, once again R1 square into L. So what will be my applied torque? Mu is what? 2 into, sorry, what is the viscosity value? 10 into 10 to the power minus 4 R1 cube. 1 cube. Length will be what? The length they have given, height is given what? 2 meter. What is that value? Pi into what? Omega. What the omega value they have given? 5 radian per second divided by what? 5 into 10 power minus 3. Check it out. All of you are getting the same equations? No, but anything we are missing over here? See, there is a 2 pi into 2 will also be there, right? Into 2 will also be there. Why? Because 2 pi r1 into L is there, right? And already we have omega value that is also equal to 2 radian per second. So both times will be there. So if you just multiply with the answer with the 2, so you'll be getting 1.256 Newton meter, or you can write 1.26 Newton meter. As I discussed in the WhatsApp group, I have given the similar kind of problem. There they ask basically the viscosity of the fluid by giving the applied torque. I'm asking you, when they have not mentioned anything about the linear velocity profile, then what about the velocity profile? When they mentioned nothing about the velocity profile, tell me, guys. See, so when they have not given anything about the velocity profile, remember, when the velocity profile they have not given, so the if velocity profile is not given, for this case, I'm talking about this case, if velocity profile is not given, then it's a hyperbolic variation. It's a hyperbolic variation. They can ask in MCQ question, right? Make a note of it. Now, why it is a hyperbolic, I will discuss at the end of the class. Let me discuss some of the few questions, few more questions, then we will see that. Now, try to solve this particular question. Yes, try to solve this question and tell me the answer. Tell me, guys, the velocity profile for the given cuvette flow, simple cuvette flow, they have given, and what they are asking. See, velocity profile is given as linear velocity profile, right? When you see at any layer, what is the velocity value? V naught into y by h. That means it's a linear velocity profile. A linear velocity profile, I told you, right? Shear stress will be constant. Du by dy mu into du by dy. If you just do the differentiation, my friend, you will be getting what? V by h. V naught is constant, h is constant, mu is constant. This means this will be constant. The shear stress will be acting in the negative x direction onto the what? Lower plate. Correct or incorrect? Shear stress is inversely proportional to h. That is correct statement. This statement is what? Correct. The shear stress is constant in the gap everywhere and independent of the y, as you can see from this equation. That is also correct. Now, when I told you in the last class, the free body diagram of the top plate fluid element, and the bottom plate, right? So what we have discussed there, we have discussed very clearly that when it will try to move in the positive x direction, the fluid element will offer resistive force in the opposite directions, like this. So say is false, right? And what about C statement? Shear stress acts in the negative x direction onto the upper plate. That is correct. Yes or no, guys? Now, can I move to the next one? Now, you try to solve this particular question and tell me the answer. A circular disc which is being given in the problem. Now, there is a circular disc in which we have the fluid, as you can see. Now, we have to rotate it by some constant angular velocity. Definitely, we have to apply some kind of torque, right, to maintain that speed. They are asking what is that viscous torque onto the disc. They are asking what is the viscous torque offered by the fluid onto the disc. This is a disc. Try to solve this and tell me the answer. Okay, let me give the option. Let me give the option. Just wait. Okay, option number A, mu pi mu r to the power 4 divided by 2h, pi mu w r to the power 4 divided by h, 2 pi mu w r to the power 4 divided by h. D option will be 0. So again, very simple question, but little bit of understanding is required. When you understood the concept of what you say in the previous problem, you might have seen the concept, right? I told you one word. We don't need to perform any kind of integration, but right now, when you just look at over here, right? When you just write this resisting torque, the resisting torque might different force into R, right? When you observe from the center of rotation, this is my center of rotation. This is my center of rotation, right? From the center of rotation, my different, all the fluids are not at the same distance. See, when you keep on moving, the radial distance is keep on changing. Definitely, we have to perform the integrations, but they have clearly, we have to assume that the whatever the small height is there, definitely we have to assume the velocity profile to be linear one. Velocity profile to be linear one. We have to assume here over here. Definitely, they will mention in the problem velocity profile has to be linear one. Mu into v by h, that is a gap because of the linear velocity profile, into radius, right? Into area. What is the area on which this forces will be acting, my friend? When you think of the area, when you draw the top view, and at any radial location, when you consider the small elemental area, this elemental area, my dear friend, which I have taken at a distance r from the center of rotation, having the thickness dr. So what is the area on which it is acting? You only try to assume, right? 2 pi r into dr. 2 pi r into dr. Right? Now, once again, yeah, correct. Once again, you try to assume what is happening over here. What is happening over here? So mu into velocity will be what? R into omega. Now we cannot write constant R into omega, right? As every fluid is having this different radius from the center of rotations. So R into omega into R, 2 pi R dr by h. This will be dt. Now I have to do the integration. So definitely from 0 to R, right? From 0 to R, I need to perform the integrations. So what I will be getting, my different? If you just do the integrations, you will be getting what? Pi into mu into omega into 2 pi integration of what? R cube into dr by h. So t will be what? 2 pi mu omega by h r power 4 by 4. So when you just do that, you will be getting the answer as A. In the earlier case, all the fluid elements are at the constant distance from the radial center of rotations, right? See, in the last problem, my friend, you assume that here, whatever the fluid elements are there, they are rotating at the constant speed, at the fixed radial distance from here to here. That mean radius. We are assuming linear velocity profile. Let's suppose, for example, this will be the mean radius. All the fluids are there at the same constant radial location. See, from throughout the length, this fluid element, this fluid element, this fluid element, this fluid element, all the fluids. See, again, you can argue, sir, what about this fluid, sir? I'm talking about when you take the mean radius. At the mean radius, all the fluids over here, over here, over here, they are at the same distance, right? R mean is what? R1 plus R2. But the gap is very small, that R1 is almost equal to R2. So you can write R mean that is equal to either R1 or that is equal to R2. Answer will not change. So no need to perform any integration over there. But here, when you focus your attention, definitely we have to perform the integrations. Right? See, at this location, these fluid particles are having what? This R. When you just change the distance, what will happen? This is having different radial distance, right? So definitely we have to do the integrations. Make a note of it. So when you just consider fluid element, for example, if I give the naming, if I give the name, suppose here it is A, here it is B. For both fluid particle A and B, the radial distance is different. Whereas in the earlier case, what we have assumed, this is a cylinder. Now A particle and B particle, they are having the same center of radial distance from the center of rotation. But now it is different. Is that clear, all of you? Tell me, guys. So definitely this question can be asked in further upcoming gate year. Is it done? Once it is done, let me know. We can discuss few more example. Done? Try to solve this particular question as a homework. Make a note of it or take a photo of this. Now there is a conical shape, right? Slight difference will be there. Angle theta will be coming into the picture. But it is in the numerator or denominator, whether it is a sine or cos, that you need to find. Once again, in the gap, you can assume that whatever the linear velocity profile is there, right? Now, all of you have noted down. Can I move to the next one? See, in all the question, you might be thinking they are asking torque. What if they will be asking the power? Torque into omega. So omega one more time it will be coming. Remember that. That will become omega square, right? See, this question I have taken from Subramanyam. There are more questions are there on this particular topic, but I will be suggesting you to solve from the Single only, right? Or maybe you can follow FM White for solving the numericals. Is it done? Can I move to the next one? No. So yeah, you can try to solve this question also as a homework and let me know in the next class the answers. Maybe you can note down the answers. I can tell you the answers. 2.66 centimeter per second. Guys, what will be happening if I consider, suppose if I will be giving you some hints, not for this question, but I'm asking you one question. For example, there is a fluid and maybe you can consider both are there in a container like this, concentric cylinders, and maybe you can think of there is a liquid over here, and then this is rotating in one direction and this is rotating in another direction. For example, both are rotating in the opposite sense. For example, there is some mechanism or by which both the cylinders are rotating in the opposite directions. Assuming the linear velocity profile, what will be my different? What you will write in the resistive force? So when you write the resistive force, shear stress into area, in that shear stress you can write V mu into what? Whatever the V we are writing, actually 2 pi, whatever the radius is there, into L. This is actually the relative speed, relative velocity. But the moment we have seen that outer cylinder is being fixed one, so we are writing only the 1V. But when both the cylinders are rotating, they will be added. The relative velocity will be added. When they will be rotating in the same sense, they will be subtracted, right? So this is some of the typical mechanics one problem for the mechanical, right? For aerospace, you can just neglect that as not that important case. Correct. As you can see, the radius is not creating any trouble for us, as R1 and R2 almost a very, very, very similar value, right? As the gap is very, very small and we are assuming linear velocity profile. Again, same problem you can solve as we have already discussed in GATE 2022. So you can note down the answer for this question also. What is the power required to overcome the viscous resistance? So note down 14.5 watt. Take a picture of this directly. Don't basically note down. Don't make a note of it, but you just take the picture of this. Done. All of you have noted down. Can I move to the next one? So now, guys, we have to just think about the rheology, that is a branch of the science which deals with the different types of fluids. Here, I'm talking about this one. Note down rheology. It is a branch of the science which deals with the study of different types of fluids in a flow. It is a branch of the science which deals with the different, with basically which deals with the study of different types of fluid in a flow. One more definition: non-Newtonian fluids. The fluid which does not obey Newton's law of viscosity is called as non-Newtonian fluid. Now there are two types of non-Newtonian fluids. One will be time independent fluids. Time independent non-Newtonian fluids. Other will be time dependent non-Newtonian fluids. But the big concern over here is that what is the relationship? So that is going to be tau is equal to A du by dy to the power n. Now, what is the meaning of A? And time independent fluids will be, note down, B plus A du by dy to the power n, where A is nothing but consistency index and what is the meaning of B? B we can note down flow behavior index. Flow behavior index. And what about n? That is the exponent, right? That is the exponent. That depends on the types of fluid, right? When I talk about the pseudoplastic fluid, for the pseudoplastic fluid, n will be less than 1, B will be 0. And by looking the nature of shear stress and rate of deformation, now tell me the slope is increasing or decreasing. For pseudoplastic fluid, the slope is increasing or decreasing. Slope is increasing or decreasing. Tell me, guys. Very high slope, very, very low slope. Slope is decreasing. Viscosity will decrease. That's why pseudoplastic fluid is also called as shear thinning fluid. What we call shear thinning fluids. Make a note of it. We also call this fluid to be shear thinning fluids. What is the example? No. It is the graph, something like this. Remember, it is like this. Slope is always decreasing, right? So, shear thinning fluid. What is the example of pseudoplastic? Tell me, guys. Anyone know that example for pseudoplastic fluid? Tell me, guys. Milk, blood, ink, etc. Or maybe ketchup also you can think of. What about dilatant fluid? Dilatant fluids, n will be greater than 1, B will be 0, mu will be increasing. See, slope is what? Continuously increasing, The slope is continuously increasing. That's why we also call that to be shear thickening fluid. What are all the examples of that? What are all the examples of shear thickening fluids? Sugar solution, right? Sugar solution. Sugar in water solutions. That you can think of dilatant fluids. No, pens will be considered whatever the you are telling about the pens, that will be time dependent fluids. Some pens are we are considering in the thixotropic fluids. What we say gypsum, whatever the gypsum paste is there and all, that is the time dependent fluids. Whatever the pens are there, that is nothing but thixotropic. What about Bingham plastic? Now, Bingham plastic is basically certain fluid which telling you that at initial for the some amount of duration we have to apply shear stress. Why we have to apply the shear stress? Now, in the Bingham plastic fluid, if I tell you the example, that is a toothpaste. Now, toothpaste is not behaving like a water, in which tube is there. Directly when you open the whatever the cap of the tube, directly liquid will come out. No, paste will not come out. We have to press it. That pressing part, we say that tau naught, right? That is the example of the Bingham plastic fluid. Can you tell me some other example of Bingham plastic fluid? Drilling mud, right? Again, you can think drilling mud as the example of Bingham plastic fluid, right? Make a note of it. So let me just clear this part so that once it is done, let me know. These are the fluids till now we have discussed, that is the time independent non-Newtonian fluids. In our whole fluid mechanics or maybe in aerodynamics, you may not be bothering about those things, non-Newtonian. Even in the Navier-Stokes also, we're directly putting the value of final formula, whatever the equation we have, that is for the Newtonian fluids, right? We don't discuss anything about the non-Newtonian because when you take the example of the aircraft, air, that is the ideal gas, we are treating like an ideal gas. Again, that is once again the Newtonian fluids. Yes or no, guys? The air which is flowing on the aircraft, what is that? Newtonian fluids, right? So there is no meaning of studying the rheology, being aerospace engineer. Of course, we should knowing this thing, but again, not required for the GATE examinations. Can I move to the next particular page? Is it done for all? Is it done? No. You try to make a note of this. So I'm talking about this time dependent non-Newtonian fluids, tau versus du by dy. So what you will observe? You will observe that this is nothing but thixotropic fluid. What we are calling thixotropic fluid. That means here thixotropic fluid means what is the advantage over here? N will be less than 1, B will not be equal to 0. And once again, you see the slope of that. Slope is higher. Slope is what? Decreasing. And slope is what? Viscosity. Whereas in the Newtonian fluids, you observe that the Newtonian fluid viscosity is not changing with respect to rate of deformations. This is called as rheopactic. A rheopactic fluid where N is greater than 1, not equal to 0. This is something like this. What are all the examples of thixotropic fluid? What are all the examples of thixotropic fluid, my dear friend? Whatever the pens are there, right? But some pens, not all, right? And what are all the examples of rheopactic fluids? Gypsum paste. That means when you try to see, when you observe the YouTube videos of gypsum paste, when you search it, when you keep on applying the rotating shear stresses, when you just keep on applying these shear stresses, what you will observe that it is become thicker and thicker. With respect to time, it will become thicker and thicker. You try to observe the experiment, right? And we know that gypsum paste, we use it for basically what? Plaster surgeries and all, basically to any parts of the body in which we have to do the plastering, there we use this gypsum paste, right? So again, in the biomedical field, non-Newtonian or branch of the rheology is a very much significant, that plays a very crucial role there, right? But for aerospace or being mechanical, we mostly talk about the Newtonian fluids, right? Once it is done, let me know. Done. See guys, so yeah, what are all the example of dilatant fluid? I have not discussed. What is that? Sugar in water solution, right? Where you can write, you can write over here. Sugar in water solution. Or you can also have sand solution. Once it is done, let me know. Now, see, try to solve this question. Sorry. See, it's a very simple one, right? Here, that is a fixed one. Bottom is fixed. So, what will be the velocity profile? The velocity profile will look something like this. Here, what we have done, a thin plate is separated from the two fixed plate by the very viscous liquids mu1 and mu2 respectively, as shown in the figure. The plate spacing h1 and h2 are unequal. The contact area A between the central plate and each fluid, they have shown in the figure. Assuming the linear velocity profile or linear distribution in each fluid, the driving force F that is going to be required that pull the plate at a velocity v, that is a constant velocity. So net force in the direction of motion will be mass into acceleration. So acceleration will be zero because A is equal to what? dv by dt. Being known that v is constant, so when you do the differentiation, that will be zero. When you draw the free body diagram of the middle plate, right? What will be the free body diagram? What will be the free body diagram, my different? It's a very simple. When the this plate is moving in the forward x direction, this plate will offer some kind of resistive force in this direction, in the negative x directions, and it will offer like this, right? Let's suppose this is f1. Let's suppose we call this to be f1. Bottom plate will offer some kind of force in this direction, that is f2, f2, right? So the net force will be what? That is equal to zero. So net force in the direction of motion will be what? That is equal to, say, this one. F will be what? F1 plus f2. F will be what? F1 plus f2. Now what is the f1 value? That is a very simple. Mu1 into, this is what? Mu1, this is what? Mu2. Mu1 into v, that is a plate velocity v by h1, right? And what about f2? Mu2 into v divided by what? h2. Getting my point? So that we have to add, we have to find the values of F, that is mu1, or maybe V by into what, mu by H1, mu2 by H2. Make a note of it. And again, we have to write the area also, right? Into area, into area, into area, where area can be written as whatever the length of the plate into what, width. No, length into width. That will be the area on which shear stress will be acting. What you have not understood, whether this particular force is clear, the force offered by the plate onto the plate in the negative x direction, that is F1. When the plate is moving like this, what the this particular plate will say, you come back once again. Getting my point? In all the previous example, we have provided the velocity and force to the top plate, fluid element, and the bottom plate. This is separately, we are discussing some different cases. Getting my point? The net force in the direction of motion. In the engineering mechanics, what you have done that? In the direction of motion, what is the force? F. F1 is what? Opposite to the direction of motion, that's why negative. F2, that is also negative. Getting my point? Yes or no? F, F1, F2. Remember, fluid is not doing any kind of acceleration. Even whatever the discussion happening, suppose at this location, even though you might be discussing drawing the velocity profile, will gonna have the same value, same velocity profile. That we say fully developed flow. We will discuss what is the meaning of fully developed flow and all. So whether you place the origin here or here, it doesn't matter, because it is not having any kind of acceleration. Just like your bike, you are moving at some speed, but after a certain point of time, you will increase your speed, by lowering the gear. Then what will happen? You will be having some acceleration, right? Further, you try to change the acceleration also, you will be having a jerk, right? But here, those things are not happening in the case of what, fluid element. For a simplicity analysis purpose, we are taking pulling the velocity, pulling the plate at a constant velocity. Remember that. If not, then definitely they have to give some time and all in the problem itself. If the fluid element is having some kind of acceleration also. Done, all of you? Can I move to the next one? Done. So we have discussed something about this. I will discuss about the ideal fluid separately, right? As of now, you just make an answer for this. Non-viscous and incompressible, right? Ideal fluid means which is not having any viscosity. No viscosity, no surface tension. They will not, density will also be fixed, constant. Right? Make a note of it. Very important. So I have given some homework problem. You try to solve, put some effort, right? Tomorrow we have class in the morning. Before that, today night, you have any another class after this. So in the morning you wake up, and you try to solve those homework problem. Maybe after the class, definitely you'll be relaxing. Then after, tomorrow morning you can just wake up early and you try to solve it. Put some effort. Okay, so make a last one as a homework one. This is again very important question. I will discuss this question also tomorrow, but you tried it. At least you try. And if you need the answer, I will give the answer also. What is the force? What they are asking? The percentage reduction, or maybe I'm giving you the answer for A part, that is a force, 57.15 Newton. At least you try A part, not now. So engineering mechanics, you can make use of some, uh, you know, application of engineering mechanics that you have covered already. So try to cover variety of problem, each and every problem. In fact, I cannot discuss in the class also. So you have to be depending on yourself to have the clarity. Make a one notebook. Suppose fluid mechanics. You start solving from the chapter number 1, chapter number 2, chapter number 3 till chapter number 10. All the problem. Don't think like a rough book, that particular book. For the first time, whenever you are solving, and all the concept regarding every question, you try to note down there itself, along with the solution. Whatever you are feeling about that topic, you make a note of it. And after that, second time when you do the revision, and when you solve, you try to increase your speed. Third time, further you try to improve your speed. Those revision time, you will feel that okay, this notes, if you are stucking in between, again you need not to go back to the lecture and see. You will only have to see what you have written in the notebook, right? Okay, this is the mistake I'm doing actually. I have written the concept there, but now I have to revise that concept. Okay, this is actually the point I'm missing. Now I need to get back to those points and then I can solve the problem, so that you can save the time actually, right? Remember, before actual gate exam, 10 times you have to do the revision for each and every subject. That is a mantra for only and only any topper you ask, whether he will be saying anything, but he might have done the revision multiple times. Without that, it is impossible to crack each and every problem in gate exam or getting 60 marks in basically aerospace in actual gate exam without proper revision, because he will not be getting formula itself in actual time. If formula itself is not coming into the mind, then how can you think about the concept? You should first play with the formulas, right? Then you think of what, all the conceptual understanding and what problems. For that, only one solution is there. Always you wake up in the morning and you try to take the empty seat, whatever the seat is there, and that particular seat without seeing the notebook. Only one time you see that, right? Second time you write each and every one. Suppose chapter number 1, fluid properties. Whatever you remember, you try to write on your own, whether it is a formula or definition. And after a certain point of time, maybe it will take 1 hour or 2 hours, and you try to match with the actual notes. If it is matching, okay. If it is not, definitely you have to work on your memory part. You have to write again and again, again and again. Just don't see and try to remember it. Try to write and then you make a note of it, and try to follow for every subject, right? Now, Note down the chapter number 2, fluid statics. Fluid statics. Now here we have to understand one more thing. Yeah, pressure. When I talk about the pressure, right, the pressure term is a very big term, right? This pressure value. So here you might be thinking, sir, this is a hydrodynamic pressure or thermodynamic pressure. As of now, we have one relaxation over here that I'm treating thermodynamic or hydrostatic pressure that to be same. But in certain situation, you cannot equate both the pressure, that is thermodynamic and hydrostatic. But in most of the cases, 99% of the cases, you will be having thermodynamic pressure that is equal to hydrostatic pressure. Can anybody tell me in the class that what is the meaning of thermodynamic pressure and hydrostatic pressure? Only this slide we will discuss and we will leave for the day, so that you will be having another class and you can attend that. First of all, note down the definition of the pressure. Pressure is a normal compressive force. You can just note down normal compressive force exerted by the fluid per unit area. And we speak of pressure only when we deal with the gas or liquid, because we don't deal with the solid. In case of solid, we will be having the stress, right? 3D compressive stress we call that. 3D compressive stress in case of fluid, we call that to be a pressure. But there is a certain difference between the pressure and the stress. Both are not same. So make a note of it. Hydrostatic pressure, my dear friend, it consists of only translational mode of energies of the molecules. It consists of only translational mode of energy of molecules. It consists of only translational mode of energy of molecules, whereas thermodynamic pressure, it consists of all sorts of energies, whether it is a translational, rotational, and vibrational, right? But in most of the cases, remember, in most of the cases, my dear friend, generally we are dealing with the translational mode of molecules, right? Basically, whatever the translational modes of the energies will be there, that we are considering. That's why we say thermodynamic pressure that is equal to hydrostatic pressure. Yeah, correct. Pressure is a scalar quantity, right? Pressure is a scalar quantity. We also call zero order tensor. We also call zero order. And the stress we call second order tensor. We don't talk about the pressure in case of solids. We say stress. So whenever, remember, whether either fluid is moving or fluid at the rest condition, always remember hydrostatic pressure will be acting. That is a thermodynamic pressure, that is a 3D compressive force or 3D compressive stresses, will be acting in a fluid element. Right? Done. What is the unit of pressure? Pascal. Yeah, SI unit is Pascal. 1 bar, we also say 10 to the power 5 Pascal, zero point 0.1 megapascal, 100 kilopascal. 1 ADM, we say 101, 3 to 5 Pascal, or 101.325 kilopascal, or 1.01325 bar. That means 1 ATM is greater than 1 bar. Yeah, 1 Pascal, we know that. 1 Pascal, 1 Newton per meter square. Once it is done, in the next class, we will be discussing the absolute pressure, gauge pressure, and atmospheric pressure, right? Thank you all. Make a note of this. Yeah. Done for all. All of you have noted down. So all of you guys got the slides right, that drive for the FM fluid mechanics, right? Correct. So in that I have uploaded the NPTEL assignment also. So meanwhile you can start solving that also. Okay guys, thank you.